If I can't picture it, I can't understand it. Albert Einstein. Welcome, students. Today, in Dynamics of System of Particles, we discuss very important idea, that is variable system of particles. Sometimes we encounter such a system of particles which continuously exchanges its particle from its surrounding. Say, for example, a rocket or space shuttle. As it proceeds in space, the fuel burnt inside the spaceship is a rocket is ejected outside as burned gases, and as a reaction force obtained from this ejected gases, the spaceship or rocket proceeds forward. That is a classical example of a system which is losing particle continuously to its surrounding. There may be a system which is gaining particle from surrounding. Suppose hailstone falling in the atmosphere. In the atmosphere, the hailstone gathers dust particle and more snow on it. So its mass increases. So that is an example of a system of particles which continuously gathers particle from surrounding. So these are two extreme examples. First one, rocket, which continuously loses mass to its surrounding, and falling hailstone that continuously gathers mass from its surrounding. There may be system which are simultaneously gaining or losing mass from the surrounding. These systems require a very special attention in the analysis, because all the principles or methods what we have developed till so far, they are based for such a system whose particles are constant, means it is not exchanging particles from the surrounding. So what we do for such system of variable system of particles? To decide this, let us first discuss in detail what kinds of this system may be. Variable system of particles. Some examples. First, discuss few examples of such kind of system. Say space shuttle or rocket that we have taken in the beginning of screen, and a system losing particles to its surrounding. This is a system of the kind which continuously loses particles to its surrounding, because when the fuel is burned, the burned fuel is ejected outside of the rocket as burnt gases. Say another example, helicopter. The main rotor or fan of the helicopters collects air outside or above it and pushes air below it. So if you consider a portion of air from the main rotor, say for this portion of air is a system. What kind of system? Air is continuously incoming inside and here going outside. So this is a system which is continuously gaining and losing particles from its surrounding. So that is a system that simultaneously gaining and losing particles. Similarly, we can take another example of conveyor belt. Say it is industrial conveyor belt. Some sand particles or say some ore or derived from the mines are being transported from one place to other place. So here from this hooper, this sand particles are falling on the conveyor belt. This conveyor belt collects the sand particles here and leaves it here. Now, if we consider this much of a portion of the sand, so this is a system of particle, but what kind of system? The particles are continuously incoming into system here and they are leaving system here. So this is again a system that simultaneously gaining and losing particles to its surrounding. Similarly, we can think of such system which can be only losing particles to the surrounding. Suppose the time when we shut off the sand particles falling from the hooper, but conveyor belt is running, so sand particle will fall down. So in this way, there is no incoming particle, only there are outgoing particles, and total mass of the sand on the conveyor belt will decrease. So this system will be what? A system that is continuously losing particles to the surrounding. So what we can say about such system? Let us define variable system of particles. A variable system of particles is a system that continually exchanges particles with its surroundings. So what is the main idea? Such system must continuously exchange particles from surrounding. Either some particles are continuously entering system or some particles are continuously outgoing of the system. Particles entering the system bring their mass and momentum into the system, and particles leaving the system leave the system with their mass and momentum. Thus, total mass, momentum, and energy of these systems may be constant or variable depending on what is input and what is output. So, total mass, total momentum, and total energy of such a system may be variable or may be constant, but usually they are variables. So, how we analyze the system? Rocket propulsion, lift of helicopter, conveyor belt are some of the common examples of this category of system. So these are the very common examples. Just by observing these examples, we'll try to develop a strategy how to analyze such kind of system. And one thing I want to point out here, actually this kind of system are usually known as variable mass system. But what I want to say here, there may be case, say a system of this helicopter, this gas. If you enclose this system, in this enclosure, you can see amount of air is constant. So mass is constant. Similarly here, if you enclose system from here to here, mass is constant. So we cannot say it is variable mass system. What is variable? Particles are varying. Few particles are entering and few particles are going in such a way that total mass of system is constant. So its actual name should be what? Variable system of particles, because variable mass may create sometime confusion that mass must vary. But for such system, mass may be a constant or may be a variable. So let us proceed further. Strategy of analyzing. How we can analyze a system? Let us see energy and momentum methods for system of particles established so far, derived from such systems that neither gain or lose particles with its surrounding. We must therefore find a way to reduce the analysis of a variable system of particles to such a system that does not exchange particles with the surrounding. So what we to do? In the variable system of particle, we must think such a condition under which the system what we are considering is not exchanging particles with the surrounding. Let us see how it can be established. Again, we discuss with terms of some example of a conveyor belt. But what we do, let us see. For the purpose, we consider a time interval and a suitable portion of the setup. All the particles which will enter the portion in this time interval and all the particles present in the portion what we have considered at the beginning of the interval constitute a system that neither lose or gain particles. I'm again saying that in such system, consider a portion of system and a small portion which will enter this earlier portion into the considered time interval. So particles of both these portions will constitute a system which will neither gain or lose particles in the considered interval. Let us try to understand this idea with the help of example of conveyor belt. The idea is better explained by the following example. What the example is? Say here a conveyor belt, we are considering it at a time t. Now consider here at time t plus delta t. So some sand has been fallen from the hooper on the belt and the same amount of sand has been fallen outside it. So how we can model it? Say here, we have this enclosure, portion P of this setup. What do we say? Consider a portion of the setup. So we have considered this portion P. Now, all the particle which will enter the portion in this time interval. So we consider some particle which will enter, or say all the particle which will enter this portion in this time interval delta t. Suppose here, this in portion Q, all the sand here in this portion Q or all the particles in this portion Q will enter P in this time interval delta t. So this all the particles within Q and P will constitute our required system. Why? Because at the end of the time interval, what will happen? This will enter here, and equal amount of particle will live here, and they will constitute portion R. So what is our system? At the beginning T, the system is Q and P. At the end of the interval, the system is P plus R. And now, how many particles and what particles are included in Q and P? The same particles are included here, P and R. So, in this way, very skillfully, we have converted this variable system of particle into a system of constant particle, means that is not exchanging its particle from the system. So in this way, if we consider such kind of system, we can apply the methods of system of particles, the energy method and momentum method, to analyze such systems. Let us see here. In the above setup, let the send in portion Q enters the portion P on the conveyor belt, and send in portion R leaves the portion P in the time interval considered delta T. So what I can again explain. We consider a portion P here, and we consider a time T and 2T plus delta T. So interval is delta T. And we consider amount of sand to be entered, or which will enter the system, this portion P in this time interval delta T. Let this amount is, or this portion is Q. So sand in portion P and Q is our system. And what we consider, as time elapses, this Q will decrease and R will increase. And at the end of this time interval, this entire Q has been decreased and the equal amount of sand has been fallen here. So what we can say, Q plus P, the system at the end become P plus R, having the same set of particles. So in this way, what we have done, our task has been accomplished, that we have conceived, or we have an idea to select some particles of a variable system of particle which will constitute a system which is neither gaining or losing particle, and at the same time which will contain the basic property of system, entering particle and leaving particle. For the time interval, sand in the portion Q and P constitute a system that neither gains or lose particles. So that was the way. The entire idea we can write in some other words also. Let us see here. In other words, to apply energy and momentum methods in analyzing dynamics of variable system of particles, we must consider the same set of particles in the beginning, during, and in the end of a time interval under consideration. So let us try to understand this. Actually, what I have done, the entire idea explained here, I have summarized here in this one paragraph. Let us see what is again. To apply energy and momentum methods in analyzing dynamics of variable system of particles, we must consider the same set of particles in the beginning, during, and in the end of time interval. Let us see how it is accomplished here. We have considered particles in Q and P. What is how many particles are in Q? That many particles which will enter the P in time T plus delta T, and which will leave the P in time T plus delta T. So in this way, what we are doing, we are considering here in the beginning, that is some set of particle, and at the end the same set of particles in the system. So in this way, we can analyze the methods what we have developed for a system whose particles are fixed. Let us see how we can analyze or apply these ideas by considering few example problems. Example 1. A horizontal stream of water flowing at velocity u in a cross-sectional area S strikes a vertical plate of mass m in free space. So that is the idea. Here this is the steel plate of mass m, and here water stream horizontally, it strikes the plate and splashes out and spreads parallel to the plate. Part A. How much force is required to hold the plate at rest? Actually, it is a very common experience that water will push the plate, so plate must proceed forward. But what is asked? How much force must be applied on the plate from this side to hold the plate at rest? And again, if the plate is at rest, we can see the water is a variable system particle, because if you consider any portion of water, the water is continuously entering the portion and continuously leaving the portion. So how we can accomplish the idea? What we consider, or we have to consider same set of particle at the beginning, during and at the end of the time interval which is under consideration. So what we do, simple idea is, we can select a portion here, this one, and a portion here which will enter this portion in time delta t. The same portion will enter here, and in the time at the end of delta t will come out here. So let us see here. Water in the portion Q enters the portion R through portion P in the time interval from t to t plus delta t as shown in the figure. So what are Q, P and R? Let us see here. So on the diagram at time t, that is portion P from here to here, and this is portion Q. So the water from portion Q must enter portion P in time delta t, and the same amount of water must leave the P in time after time delta t, and which has leave the portion P, we have termed the portion R. Let us see in this diagram. So P and that is R. So in this time, in the beginning of this time interval, that is Q is to enter the P, and at the end of time interval, Q has entered and equal amount of water has leave or exit from point P. So this amount of water, the same water molecule are here in this portion. So in this way, our system is changing shape, but what we are considering, same set of particle from t to t plus delta t, or in the beginning of interval, during the interval and at the end of interval. So that is the idea. And in such kind of problem, that is simplest idea or most logical idea which we can consist, or an idea which we can apply to any kind of problem of variable system of particles. The system of particles consisting of the portion Q and P at the beginning of the time interval takes shape of portion R at the end of time interval. Thus, it is a system that neither gains or loses mass in the time interval shown. Just see the idea we have explained. So what we can do? In addition, velocity of the water particles in the portion Q is horizontal and in portion R vertical. So here the velocity of water in this way, or in this portion velocity are in this parallel to plate, so it is vertical direction. Here vertically upward, here vertically downward. And now we have to consider system in free space. So there is no gravity. Now what we do? The simple idea is we can apply impulse momentum principle, because that is time of that is velocity vector change and time interval. So this problem relates what? Velocity change and time interval. So this is area of using impulse momentum principle. And how we can apply impulse momentum principle? Let us see. Apply the impulse momentum principle on this system for horizontal components. Actually, we have to apply on the plate horizontally. So if you consider horizontal component, in this way, the impulse of horizontal applied force will be there. So how we can see? That is the portion in the beginning of the time interval Q and P. The entire amount of Q will enter P, and at the end it will come out. So here we have to consider momentum of this portion only, because this portion remain intact throughout the interval. So its momentum of this portion is not going to change. Suppose mass in this portion is dm. So how much momentum? dmu, because velocity is given is u. Now let us see the impulse of forces. Now on this portion, that is suppose a force F is applied on the plate. Now plate is rest. So equal and opposite force must be applied by water on the plate, and the plate must apply equal and opposite reaction. So we are considering here the reaction force of the plate on the water, and for this time interval that is sufficiently small, and for this time interval this force may be considered constant. Actually it is constant. So even though if it variable, for this sufficiently or infinitely small time interval, it may be, its variation may be assumed negligible, so it may be assumed constant. So we written impulse F into delta t. Now it will be final momentum. So this portion has entered here and equal amount water lived here. Now momentum of portion P is not changed. It remains same. You can realize how particles or in portion P are moving. In the same way they will keep on moving. And in portion R, the water is coming here and coming here. So here we can say there is no horizontal component of momentum. So by representing the x direction horizontal and y direction vertical, we can write x component impulse momentum equation. What is that? Pix plus summation j I to fx is equal to pfx. Here, this is what? Initial x component of momentum. That is total impulse of horizontal forces, and that is what? Final x component or final horizontal momentum. Now you can see from here, initial momentum is dmu and impulse is only here f dt, so it will be in minus direction. So what we have here, dmu minus f dt, and you can see here no horizontal component of momentum, so right hand side will contain 0. So what we can write, dmu minus f dt equal to 0, and from here we can write f is equal to dm by dt into u. The only way, the only task is remaining. What is dm? Dm is the water contained in portion Q that will enter the portion P in time dt. And we know that every water molecule had velocity here u. So all the molecules on this line have velocity u. So in time dt they will travel a distance u dt. So this length must be u dt. So this length is u dt. Cross section area is S. So what is volume? S into u dt. And if you multiply that volume by density rho, what you get? dm. So dm is rho into s u dt. Let us substitute this value, and what you get? Rho s u dt upon dt into u. Dt will cancel. So what you get? F is equal to rho s u square. So that is required horizontal force to maintain or to keep the plate at rest. Now let us see what is asked in B part. How much force is required to maintain the plate moving with a constant velocity v towards the right? So now we have to maintain the force in such a way that the plate must move towards right with a constant velocity v. So how we can solve it? Again we make the same strategy. What? Apply the impulse momentum principle for the horizontal component on the system consisting of water in the portion P and Q. And water in portion Q is sufficient, or that amount of water which will enter the P in the time interval delta t. So that is Q and P. And its momentum is dmu, as because we are not writing momentum of the water in portion P because we know that it is not going to change. So we write only momentum of water in portion Q, that is dmu. And we write impulses of the forces here, f dt. And this is the force of reaction between the water and the plate, because plate is moving at a constant velocity. So net force on the plate must be 0 in horizontal direction. So what the force is applied on the plate, the same force must be applied by the water on the plate, and the plate must apply the same force. So what is the force required to maintain the plate moving with the constant velocity? The same force plate will apply in the water, and we're writing impulse of that force here. And equal to, what is there? Now this plate is moving with velocity v, so this portion in R is splashing out vertically parallel to plate as it was earlier, but it will have velocity v together with the plate because plate is moving here. So this portion, both this portion will have velocity v. So these two portions have here total horizontal momentum, that is dmv. So now you can see, and let us write equation for x and y component. We show the x horizontal direction and y vertical direction. So what is impulse momentum equation? Pix component plus summation j I to fx is equal to pfx. Again, initial x component momentum, that is total impulse of all the external forces in the x direction, that is final x component momentum. You can see this is what dmu. This again here f dt in opposite direction, and here x component is dmv again. So let's substitute value, dmu minus f dt is equal to dmv. So from here what we write? F is equal to dm by dt u minus v. Let us see equation number 1. Again the task is remaining to substitute the value of dm. Here dm will change from previous problem. How? In the time interval dt, a length u minus v dt of the water stream enters the portion of P. Therefore, why? Actually, the plate is moving with velocity v and water is moving u. So what is velocity of water with respect to plate or with respect to this line? That is u minus v. So this length u minus v dt of water will enter the plate. So what will be dm here? The rho s u minus v dt. You can see. Now we substitute this value here. So what we get? Substituting dm from equation 1 into equation 2 we get, or you can say substitute dm from equation 2 into 1, or you can put dm from this to that, you will find the same thing. So what we have here, f is equal to rho s u minus v dt upon dt into u minus v. So f is rho s u minus v whole square. Now this is the force, and you can see the force has been reduced, but again it is a constant. So in this way also, water stream is applying constant force on the plate, and the same force has to be applied externally, but this force is somewhat reduced from the earlier case. Now again, the only task in analyzing such problem is to assume a system which is neither gaining or losing its particle from surrounding in the time interval considered. And in most of cases, we will apply momentum method. In some cases, it will require energy method. We will apply the energy method also. Now let us come another example of the same category. And again, what I recommend you, try to understand how we consider the system. What in all the problem, what we do? We consider a system portion P and a portion P which will enter in the time delta t. And at the end of delta t, the P will enter and leave. It will become a portion R. So in the beginning, the system consisting of portion P and Q, and at the end, the portion consisting of or system consisting of portion P and Q will constitute our system or desired system which has neither gained or lost particle from its surrounding during the considered time interval. Say for next example, say example 2, a uniform rope of a linear mass density lambda is held above a horizontal floor with the lower end of the rope touching the floor as shown in the figure. See here, a uniform rope is held here above the floor and the lower end of the rope is touching the floor. Find the force exerted by the floor on the rope as function of time after the rope is released. So here we have to measure time when the rope is released. Now it is common experience what we can visualize that as the rope is released, it will fall down and here it will gathered in a heap. One thing, actually rope is extremely flexible, so no force is applied on the falling rope by the heap. There is no force of interaction, but the falling rope will apply force on the heap. Why? It will fall and strike and lose its momentum. Now just see here, and again in this problem, the how much heap is gathered, the size of heap or height of heap we have to ignore. Actually, or we can say we have to assume very thin and very long rope. How we solve it? Say at the beginning t is equal to 0, the rope, the entire rope length is straight. Now when it is released after time t, some portion has been fallen and that portion fallen has been collected here. This length has been collected here in the heap, and again what we have to neglect the height of the heap. So in time t, the portion fallen is half gt square, very simple, because the rope is in free fall. Here there will be no vertical force on the straight portion, but as the rope fall on the heap, it will lose its momentum, so it will apply some force on the heap. So the portion which has fallen on the heap, there is force between that portion and the heap, but there is no force between the vertical portion and the heap because the rope is extremely flexible. Now the entire vertical rope is moving with the same velocity. Of course, that velocity is variable. As time increases, that velocity increases because it has the acceleration g. But every point on the vertical portion of the rope has same velocity and all the points in the heap has zero velocity. So let us this velocity is v, and we can write very easily v is equal to gt. So that is here. Now what we have to consider system? We consider the heap as portion P and a small amount that will enter in time dt the heap as Q. So that is, this portion is Q and heap is P. Consider the portion of the length v dt immediately above the heap this portion enters the heap and become part of the heap in the time interval from t to t plus delta t. The required system that neither loses or gains particle in the time interval dt consists of this portion of the length vdt and the heap. So if you try to find analogy from the previous problem, the heap is p and this is q. And this is a system which neither gaining or losing particle, this portion. Now let us see how we can apply the impulse momentum principle, because again, before the beginning of the time interval, this dt, this portion was having velocity, but this portion was rest, so this portion was having momentum. But at the time end of this end reaches here, become part of heap, and it will lose all the momentum, so there is no momentum. So that is a situation of momentum change in time interval. So again, area of impulse momentum principle. Applying the impulse momentum principle on this system of particle for the time interval t to t plus delta t, what we get? See this and this portion has momentum. What? Its mass will be lambda vdt and v. So vdt is length, lambda is linear mass density, and v. So that is entire momentum. And this portion heap is at rest, so it has no momentum. So the entire system has momentum this at the beginning of this interval dt. Now we apply the impulse of all the forces. Now see, here impulse of the force from the ground rdt and impulse of gravity. So let us as compared to weight of the heap, we can ignore the weight of this portion. So we are considering weight of the heap only. How much rope has been collected in the heap? This much length, half gt square. So if you multiply this length, half gt square by lambda, that is mass of the heap. And if you multiply that by g, that is weight. So lambda into, you can see, half gt square into g into dt, that is impulse of gravity. Now you can think that impulse momentum principle, we usually ignore impulse of finite forces in impulsive event. But actually here we are not required to find what? Momentum. We are required to find force. So let us consider, and after dividing delta t, you can see this delta t will be divided, and now we will get a finite force. So here it is not necessary that always ignore the that is the impulse of finite forces. Actually try to consider them. If they are negligible, only when ignore them. Now final momentum is 0. So we are not showing any momentum here. So designating here the vertical and horizontal component, we can apply the impulse momentum principle. Here what I have mentioned earlier, that R is the reaction force applied by the heap. Now here we can say vertical y and horizontal x. So in this situation, we apply the impulse momentum principle for the vertical components. So Piy plus summation ji to fy is equal to Pfy. That is initial y component momentum. That is a net external impulse or net impulse of all the external forces in the vertical direction or y direction. And that is final y component momentum. And that we know that lambda v dt v, this, and it is minus. This again minus, and this impulse is positive, and this is 0. So let's substitute the values. So what we get? Minus lambda v dt v and minus lambda half gt square g dt, and g we can say g square, so here g square, and that is positive, so it is 0. Now what we do? From entire equation we can cancel out dt and write value of r. And at the same time we divide dt, and v is here. So for v, substitute v is equal to gt, and we substitute v gt, cancel dt, and find r. So r you get 3 by 2 lambda g square t square. So that is reaction force of the floor on the rope. Again see, the same situation or this situation we have also analyzed by the same strategy with which we have analyzed the previous problem. Actually, what I have seen in our textbooks, such problems are solved at several places, random methods. Of course, that methods are very beautiful. I'm not discarding those methods. But in the beginning, if you have a systematic method for a particular type of problem, it is better to develop understanding. And later on, when we become mature in understanding, you can skip several steps on this method and you can apply, you can write this portion very quickly. And that is what such kind of method are presented in textbook. But for the understanding, consistent understanding, what I am saying, consistent understanding means whatever we have learned till so far, we are applying the same thing what we have learned and solving the problems to come. This is the only way how we can solve variable system of particles. Now, let us come on another very important idea of that, rocket propulsion. Actually, rocket propulsion is a system, or rocket is a system which is continuously losing mass to its surrounding. So, example 3, rocket propulsion. What we assume here, consider a rocket of initial mass m0 in a free space. At an instant, during its flight, the rocket ejects the gases produced by burning its fuel at a rate r kg per second, means the rate of mass rate of the fuel which is burned is r. And the ejected gases leave the rocket at a velocity u relative, or v relative with respect to the rocket. What is given? Initial mass of the rocket is given m0. And rate at which fuel is burned is r kg per second. So it is what? Rate of decrease in mass of the gas rocket. And how much fuel is burned? The same amount of fuel is ejected from the nozzles in the rocket as ejected gas or burned gases, and these gases have velocity v relative with respect to rocket. So these ideas given, and we have to calculate first. Deduce suitable expression for the thrust force on the rocket. Actually, what amount of force the rocket is gaining by throwing the gas backward. This force is called thrust force, or the reaction force between the rocket and the ejected gas is the thrust force. So first we have to develop a suitable expression for this thrust force. Again, we use the same strategy. At the beginning of a time interval from t to t plus delta t, velocity of the rocket is v and mass is m. In this time interval, let dm mass of the fuel is burnt and ejected as burned gases with a velocity v escape with respect to ground. Here we write v escape or ejected gas with respect to ground, and velocity of rocket changes from v to v plus dv. What we assume? We assume a time interval, time t, after rocket has started, it has acquired a velocity v, say. At this time, its mass is m. Now, in a small time, t to t plus delta t, or delta t time interval, dm mass of the gas has been burned, or fuel has been burned, has ejected, and it is ejected with a velocity ve with respect to ground. And at the end of this time interval, rocket has acquired a velocity v plus delta v. So at the beginning, this rocket has velocity v, and at time t plus delta t, rocket has acquired a velocity v plus delta v. dm mass of the fuel has been burned, so mass of the rocket has become m minus dm, and dm gas has been ejected here, and its velocity is v with respect to ground. Actually, I'm writing here v relative because we want to write impulse momentum principle. So we have to write momenta of each and every constituent part with respect to ground or the free space which is given. So the required system that neither loses or gains particle is the rocket with its unburned fuel at the instant t. So what is the system at time t? The rocket and unburned fuel. So only this portion, and let us see it this way. The rocket and unburned fuel, or that entire mass, is included in this boundary. So this is our system of interest at the beginning of the interval. Now actually there are no incoming particle, so we don't consider a portion like q what we have considered in previous problem, because in previous problem there were entering particle also. So what we considered? A portion of system and portion to be entered in time delta t. But here there is no portion to enter in time delta t. So we consider only the portion at the beginning here. Now what we do, consider what will happen in after time interval t plus delta t, at the instant t plus delta t. This system consists of the rocket, fuel inside, and the ejected gases in this interval as shown in figure. So at t plus delta t, if we consider the entire or the same set of particles which were there inside, what they are, the rocket and the remaining fuel and the burned fuel which has been ejected as gases here. So this rocket and this is the system here. So this way. So that is system. Now you can see, I'll again write here why we have written this velocity with respect to ground, because we have to apply method of impulse momentum or momentum method. For that, we are choosing here the reference frame given, in which velocity of rocket we have to find, and that is reference frame of the free space. And just see a little bit consideration here that there are no external forces on the system. So momentum of system will remain conserved. So what we apply here? Conservation of momentum. As the rocket is in free space, there are no external forces on the rocket. The linear momentum of the system must remain conserved. And how we can write the momentum conservation equation, let us see. Applying conservation of a linear momentum on the system of interest, we get, what is system of interest? At t, the rocket and fuel inside. At t plus delta t, the rocket and remaining fuel and the ejected gases in time delta t. So we have again redrawn the same diagram. Now say x and y. So which component momentum we are interested? Only y component. So summation piy is equal to summation pfy. That is equation of conservation of momentum. So what is initial momentum? That is what we consider at time t mass was m. So mv is the momentum. And what is final momentum? Mass of rocket is m minus dm and velocity is v plus dv. So momentum of this portion rocket will be what? M minus dm into v plus dv. And momentum this portion dm and ve, that is in minus direction. So what we have? mv is equal to m minus dm into v plus dv, this portion, and minus dm ve or ve dm. Now just by solving it, this what we get? 0 is equal to minus v dm plus m dv minus v dm. There is no difficulty to solving this. What? This m into v product will cancel out and the remaining term we have written here. So now just and again one thing, there is a term dm into dv product. So we always ignore the product of two infinitely small quantities because they are always negligible as compared to these terms. So we only these three terms are remaining. Now we have to incorporate v relative because v escape here, this is not given. So we have to write v ejected gases in terms of v relative and velocity of rocket. Substituting v escape is equal to v relative minus v in the above equation, we get. Why this? Actually, this is velocity with respect to ground or free space, and velocity of rocket is v plus dv, or we can write v. So what is v relative? They are in opposite direction. So v relative will be this velocity plus this velocity. So ve plus v is equal to v relative. So what is v? V relative minus v. So there is very simple way, and we substitute v relative minus v for v dm. So what we get? mv dv is equal to v relative dm. Why? Actually, if you write v relative minus v, so v relative dm minus n plus v dm. So minus v dm and plus v dm will cancel out. So we have two term only, m dv minus v relative dm. So what we get? m dv is equal to v relative dm. Now by dividing both the sides by dt, what we get? m dv by dt. dv by dt is acceleration of rocket. So m dv by dt is the net effective force of the rocket. And what is net effective force on the rocket? This. And that is from the gas. So this is the thrust force. Let us see. Dividing both the sides by dt, we get m dv by dt is equal to v relative dm by dt. The left hand side represents the effective force on the rocket. Therefore, the right hand side is the thrust force F on the rocket. So what we can write here, F is equal to V relative dm by dt. Here we have considered the thrust force will be upward, so that is magnitude. And this is what magnitude. And what is dm by dt? Dm by dt is the rate at which fuel is being burned, the R which is given. Here dm by dt is equal to R is the time rate at which mass of the rocket decreases. So we can write here R also, but I am writing here dm by dt. One more thing. Actually, the thrust force is opposite to V relative. So to write exact relation, we have to put here a minus sign. Since the thrust force is opposite to the direction of V relative, we should write what? F is equal to minus V relative dm by dt. So that is expression for the thrust force. What this minus sign shows? This minus sign denotes the direction of thrust force is opposite to velocity of the ejected gas relative to the rocket. So that is what the idea. The first part has been solved. Let's see what is the second part. Assuming the rate R of the burning fuel and velocity V relative of the ejected gases with respect to the rocket to be constants, deduce suitable expression for the velocity of the rocket as function of time. So what we to assume? We to assume the rate at which the fuel is burned or rate of decrease in mass R to be constant and velocity of the ejected gases related to the rocket to be constant. And assuming these two things, we have to find or write a suitable expression for the velocity of rocket as function of time. So what we do? Thrust force on the rocket, that is F is equal to minus V relative dm by dt. This is constant and is given. And what we can write here for F, m dv by dt, because we have to write velocity. So force we write mass into acceleration, and acceleration is dv by dt. So we incorporate here velocity of rocket. So m dv by dt is equal to minus V relative dm by dt. So what we can write here? dv is equal to minus V relative dm by m. So that is not a very difficult, simple algebraic manipulation. Now we incorporate definite integral. This v naught to v dv is equal to minus V relative integral m naught to m dm by m. Actually, we are considering a time interval from beginning, and we are considering here when in the beginning mass of rocket was m naught, velocity was v naught. Of course, it may be 0, but we are assuming here v naught. And when the mass becomes v at time t, velocity becomes v. V relative is constant, so we have taken it outside of the integration sign. And now you can see both side integrations are very simple. It will be v, it will be ln m. So what we have, v minus v naught is equal to minus V relative ln m by m naught by incorporating the limits of integration. Now we know m is smaller than m naught, so this will be negative. So we just reciprocate. So what we m naught by m. So what will be positive V relative ln m naught by m. So what we have, v is equal to v naught plus V relative ln m by m naught. So v is equal to v naught plus V relative ln m naught by m. Now we can write for m as R, rate of burning or fuel or rate of decrease of mass of the rocket is constant. So m will be m naught minus RT, because R is the rate in time t. RT mass of the fuel has been burned and ejected out the rocket. So remaining mass will be what? M naught minus RT. So let us substitute this as the rate R of burning the fuel, that is rate of decrease in mass of the rocket is a constant. We can substitute m is equal to m naught minus RT. If we substitute, what we get? V is equal to v naught plus V relative ln m upon m naught minus RT. So that is required relation, velocity of rocket as function of time. So what we have seen today, how we can analyze variable system of particles. I am giving it name, variable system of particle, not variable mass. You can see mass may be constant, as in the case of conveyor belt, mass was constant. So what is there in all the problem? The system is continuously gaining or losing or simultaneously gaining or losing mass. To analyze a system, what we do? Because all the energy methods or momentum methods or impulse momentum method, what we have developed till so far, they are based or they are derived for a system of fixed particles. Fixed particle means not mechanically fixed. Means particles must be same throughout the interval. And for the purpose what we are doing, we are assuming a portion of system and a portion to be entered if particle is entering as a system, and the entering particle must be the leaving particle at the end of time interval. We have done in the previous example. Q was portion of particle which will enter in time delta t, and P was the portion we have taken, and at the end of interval P has entered and became R. Or in other words, what I mentioned earlier, in the beginning, during and at the end of the time interval, we must consider same set of particles so that we can apply the principle what we have developed. So that was conclusion. In the next lecture, we'll meet and start discussing about rotation motion. So thanks for patient listening. We'll meet in the next class. The words of a language, as they are written or spoken, do not seem to play any role in my mechanism of thought. The physical entities which seems to serve as elements in thought are certain signs and more or less clear images. Albert Einstein.